Hey everybody, welcome back. Today is going to be our last video recorded lecture. We're talking about the ANOVA analysis of variance today. Hopefully this will help us dig deeper into our understanding of the theoretical basis of parametric statistics, but also it should ideally clarify some things regarding how we think about the stats that we saw in our linear regression unit last time. So let's get started. Just get my screen share going here. Okay, cool. All right, finally, we can talk about the analysis of variance, something that I think is a pretty useful statistical tool. We've already talked about it a lot. We've seen some examples, and now we're going to dig into the theory and look at some more use cases and examples that we will then obviously practice in class. So when do we use ANOVA? We're going to talk about this at the beginning of class. What's it for? What does it measure? So if you want to think about it just on your own real quick, you should pause the video and write down what you think ANOVA is, what it's for, and what it measures. All right, I am going to keep going, but again, pause the video if you want to think about this without having the answer. Analysis of variance pretty simply is used when we want to compare means, basically the mean responses of more than two groups, more than two populations, something like that. It's a natural extension of the t-test. It's the exact same thing, really, only instead of looking at just the difference between two groups or populations, we're looking at the difference between multiple groups and populations. We use ANOVA instead of t-test just about all the time. And in fact, you can run an ANOVA instead of a t-test if you only have two groups, and that is totally fine. What ANOVA measures is basically the ratio of the variation or the difference between groups to the variation or the difference within groups. So we're looking at our mean and our variance for each individual group and saying, like, do these differ from each other? And how much more do they differ from each other than the overall variance within a group? So if we have a lot of variance within our group or a lot of error, we have uncertainty in our measurements versus if we have a really clear error, our mean and error bars, and there's like an obvious difference, that comes out as a much more clear answer. And the reason for that is because the stat that underlies the ANOVA and the t-test also is this ratio of between group variance to within group variance. And we're going to dig into how that works with math in a minute, but that's the simple way to think about analysis of variance. It is like, I would say maybe a gross oversimplification if you're, PhD statistics person, but none of us are that. So for our sake, for understanding it and for using it, this is basically what it does. It's based on this thing called the F statistic, which is summarized pretty simply as, again, variance between groups divided by variance within groups, or aka the residual variance. So this is a simple ratio. The higher the F, the more statistical power we have. The lower the F, the more uncertain we are. So if F is close to 1, we really don't, even if the p-value is significant, we might say that if F is close to 1, we don't really have a ton of power, and we may want to be careful with our interpretation. But if F is relatively large, we might say, yeah, this is definitely a difference. We can look at some examples later. So think about why we can't just compare two means at a time. Why can't I say I have 4 means? I want to compare mean 1 to mean 2, and then I want to compare mean 1 to mean 3. We can do that with the t-test if we really want, but what we're not able to do then is see what is the overall effect of that variable y on all of our populations, and is that effect significant? And if so, what's the magnitude and direction of the individual effects? It's just really inefficient to do it this way with all the t-tests, and it also misses out on that overall effect. So we're going to look at some ANOVA tables and understand that a little bit later. So let's talk about hypotheses. We are in research design, right? So we're always thinking about designing an experiment and testing hypotheses. And we've been learning that statistics are a great tool for testing hypotheses, and that given your hypothesis, you may need a certain kind of test, and you also may need a certain kind of experiment, right? So the general hypothesis for ANOVA is Basically, the H naught is that however many groups we have, there's no difference between their means. And the alternative hypothesis would be at least one of those means is different from the others, and we might have some idea of the magnitude and direction of those differences if we so chose. But the general null hypothesis is there's no difference, like always, the hypothesis of no difference. Rejecting the null hypothesis would mean that at least one of our means is different from the others. We could then say there's a significant effect of y on x. So we should take a look at an example. Here's an example of an analysis of variance. So we first look at our graph, and then we look at our stats. With the power of the two combined, we can interpret our data. So we have a simple box plot here, which we've talked about before is not the perfect way to show data, but it will work. And we're looking at the iris data set, so we can see our 3 different species of iris. And we're also measuring basically the effect of different species on petal length. So do the different species have different length petals? By looking at the graph, we can see that Setosa has smaller petals than versicolor and virginica, that the distributions and the means don't overlap at all. Like that's definitely going to be a difference. Is versicolor different from virginica? We might say there's a pretty good chance, yes. The mean responses of the two, we can see here, this is the median and this is the median. So the measure of the center, they don't overlap, right? And we do have some overlap of the first and third quartiles here, but it's not super huge. So maybe they are significantly different, right? So we're left with a little bit of uncertainty by just looking at our visual. So then we can run the stats. And that's what we've done over here at the left. We've run the following statistical analysis, AOV, or analysis of variance, for y by x, and that's petal length affected by species. And what we end up seeing here is that when we run our summary, which is how you get your useful information out of your AOV call, we'll see that there actually is an overall effect of species. So there is a significant effect of species on petal length, which means that at least one of those species differs from at least one of those other species. Now, that's great, but it's not all of the information. In fact, almost never do we only care about this. So if you run analysis of variance and say, yeah, there's an overall effect of some variable, like that's great. But that is not what we really care about. We really care about the magnitude and direction of the individual effects on the individual groups. So tell me what those are. How you do that, we know that species has a significant effect on petal length, but how you do the different group effects is you have to run a post hoc test, or a test that you run after the first test. This post hoc test is called a Tukey's honestly significant difference test. And we are going to dig into that. But first, we need to finish our conceptual understanding of ANOVA by talking about the assumptions of ANOVA. We've already kind of seen all of these before. The assumptions of ANOVA, we have to make sure we at least think about these. We have to have independence of observation. That's a hard one to test. You have to just think about the experimental design. No outliers. We have to have normality. All data are approximately normally distributed. And we also have to have homogeneity of variance. Just like with the t-test, there's times when these assumptions can be ignored. We're going to discuss these in the lab. And if you look at the lab materials, I do discuss these. The only assumption that we can't violate ever is that independence of observation. If we have sufficiently large N, the other 3 can be violated and we're robust to those violations. But we should also think about testing them, at least to start with when we're first learning ANOVA. And I walk you through how to do that in the lab materials. Okay, so we have talked about and kind of hinted at the fact that ANOVA is paired with the Tukey's honestly significant difference test. Before we really dive into the interpretation and the use of ANOVA plus Tukey, we really do need to understand how ANOVA works in more statistical detail. So let's do that now. Here's how ANOVA works. Even if all the groups in the study have the same true mean, the data may still show different sample means for each group due to sampling error. We've talked about sampling error already. Basically, your population or your sample may not be representative of an individual full population. If we take lots of samples, we talked about this a lot. If we have sampling error, it means basically that there's a chance that our sample doesn't represent the true mean. ANOVA allows us to estimate how much variation among group means should be present from sampling error alone, not alone, if the H naught is true. If there really are no differences among populations, then taking a random sample from each population is equivalent to taking the same number of random samples from a single population. Maybe that makes sense, maybe it doesn't. But basically, if we have 3 populations and there's no difference between them, then taking 5 samples from each is the same as taking 15 from a single population, if there's really no difference between the populations. So that basically means we can pool our data. If we see that the populations are not different from each other, we can actually pool our data together. That could be useful to you someday in the future. Let's draw it out. Just kidding, I don't actually draw it out. If you would like to draw a distribution, you can. Otherwise, we'll talk about it in class. So if the H naught is not true, which means that something is different, there are real differences in means among our groups. There's likely still differences in among sample means caused by chance, but in addition, there are also differences among sample means caused by real variation. So basically what I'm saying here is like, if the H naught, if we're not able to, we fail, or if we reject the H naught, there's a difference between some of our groups. That's the short version of this. This is all like statistical language coming out of like the textbook. So that you can see what this kind of language looks like and sounds like, because you are going to see it in published papers and also in statistical texts that are trying to help you understand and learn how to use these concepts. So the short version of all of this is ANOVA allows us to determine whether there's more variance among sample means than we would expect by random chance. If that's true, we have a difference between our populations or between our samples. ANOVA is based on these mathematical terms that are new to us. So just bear with me here. I know that there's a reason why these are recorded and why we're not doing it all in class. And that's because there's a lot of detail here. And like, it's not necessary to know every single step to analyze data using ANOVA, but this is really good background for those of you who are curious, and also for those of you who are trying to really deeply understand how this process mathematically is laid out. So ANOVA is based on the group mean squared and the error mean squared. That's MS groups and MS error. Let's talk about MS groups first. MS groups, or groups mean square, is the variation among sampled subjects that belong to different groups. This is the between group variation. How much variation is there between groups? The error mean squared is the variance among subjects that belong to the same group. Okay, this is equivalent to the pooled sample variance for 2-sample t-test, if that's something that you remember. But these are basically the 2 things we're looking for: the variation between means within between group means and the variation within a group. We use both terms in our statistical test of H naught, which is just basically calculating the F, or the F ratio. The comparison of these mean squared terms is the F ratio. F equals MS groups divided by MS error. It sounds really simple, and in fact it is, but calculating each of these individually is actually not so simple, which is why we get to be thankful every day that we have statistical software that will take raw data and generate these distributions and these terms for us, calculate F, and spit out answers pretty quickly. This allows us to really revolutionize our workflow and actually do a lot of different explorations of our data in really fast, relative to previously, really fast amounts of time. So now we're going to talk about this thing called the sum of squares, which is not the same thing as the mean squares, but it's building us towards the mean squares. Okay, so calculating sum of squares. One observation equals yij, where I is the group and j is the individual within a group. So one individual y lies within the group I and is the individual j within group I. And there could be any number of groups and there could be any number of individuals. And okay, y bar, that's the grand mean of all data. And I'm drawing it out, I'm calling it y bar instead of drawing out a y with a bar on top, just so that people are less confused about some of the statistical notations, and also because that symbol wasn't available in PowerPoint. Yay. So sum of squares, or SS, is equal to our individual observation minus y bar. That's pretty classic, right? And that is equal to yij minus yi, which is the group mean of I, plus y bar I minus y bar, where y bar I is the mean of the group. So the difference between each observation and grand mean is the individual value in a group minus the group mean plus the mean of a group minus the grand mean. Fun, right? So fun. That's how you calculate your sum of squares. Okay, now we're trying to calculate the mean squares, and we're still now looking at this sum of squares calculation. So it's going to get a little confusing, but here's the formula for sum of squares at the top. Sum of squares is here. This is MS groups. This is MS error. And I obviously cannot draw, but you get it. All right. Sum of squares is here. Here's our mean squared groups and our mean squared error. So it's just kind of a depiction of the portions of these things. The vertical lines here are deviations, as you know, from one point to the grand means. So here's the totals, and here's MS. So here's the grand mean, and each one subtracted from the grand mean. Here's MS groups, where we've taken the mean of each group, and that's the horizontal bar, and we're subtracting that out from the grand mean. And then here's the error one, where we're taking the individuals and we're subtracting them out from the mean of the groups. So we're calculating the difference for error term between each individual observation and the group mean. And then for the groups term, we're calculating the mean of each group, and we're subtracting that from the grand mean. And then for the total, we are calculating the difference from each individual observation to the grand mean. So we need all three of those to finish our calculation. Okay. Now the group mean, or the MS groups, is represented by this y bar I minus y bar. So we're subtracting the mean from each group from the overall mean. And then the error, which is represented in red here, shows us the difference between each individual term and the population level or the group mean. Okay. And then the total, that is at the left of the equation. All right. So we repeat this formula. This should say calculating the sum of squares, by the way. But this is mean squares groups and mean squared error as well. We repeat the formula for all observations, then we square the deviations and add them together to get the sum of squares. We've introduced the sum of squares topic previously when we were talking about the linear regression, but how to calculate S, right? So we calculate our deviation for all of our observations. We square those deviations to make it S squared. And then we add them together, right? All the S squareds for all the observations. And that is our sum of squares. So the formula for sum of squares thus looks like this. And this is a little bit washed out from multiple copy and pastes from the textbook. So sorry about that, but hopefully you can make it out. Sum of squares total is the sum of all observations in I and all observations in J. We're taking yij minus y bar squared. So we're taking our difference, and that's our S, we're squaring it. And to break that out into smaller pieces, you can see the sum of squares within with the sum of squares error, and then the sum of squares groups. So these are the two calculations that you saw on the previous slide, which is here, groups and error. Yeah, square those and add them together, and you get your SS. And here's a way to calculate the grand mean, which is super fun. But you already know how to do that, right? It's number of observations in each group times the mean. You sum those together, divide that by n. This is just calculating an average. You could just take the average of all of the observations in all of the groups as well to get the grand mean. They're both the exact same. Okay, so finally we have SS total, which we're going to use in our ANOVA calculations. Okay, so we've calculated sum of squares, and we've talked about sum of squares groups and sum of squares error, and now we're going to talk about mean squares. And I have a typo I just want to point out right here. Sum of squares should be here. We are working towards calculating mean squares, but right now This is sum squares. Okay. So if you're confused, that typo is really important. I'm really sorry that I made it, but I had already started recording and now I feel like I shouldn't fix everything and make it look different than it looks in the recording. Okay. So here we go. Group means squares, MS groups. That's what we're doing next. We've just done SS total. We've talked about SS within and SS between. Now we're moving on to mean squares groups. These are the things we actually want to get our F ratio, and we need SS to do it. So we have mean squares groups, the variation among sampled individuals belonging to different groups, aka the between group variation. Looks like this. To calculate MS groups, we need the sum of squares groups, which we just calculated, and we divide that by the degrees of freedom groups. And degrees of freedom is just k minus 1, where k is the number of groups. So this is the same as degrees of freedom equals n minus 1, only in this case, we're using k instead of n because statistical language is confusing. K is just the number of groups. So if we have 3 groups, our DF is 2. If we have 10 groups, our DF is 9. So we're taking that SS groups that we calculated prior, dividing it by DF groups, and that gives us our MS groups, or our mean squares groups. And that is the numerator in our F ratio. Okay. MS error, on the other hand, is the pooled sample variance measured, which is a measure of variance among individuals in the same group. So the within group variation. MS error equals the within group variance, right? So MS error is the SS error, which we just learned how to calculate, divided by the degrees of freedom for error. Now, the degrees of freedom for error is a little complicated. It's the sum of ni minus 1, which is the same of n minus k, where n is the grand sample size, the total number of samples in all groups, and k is the number of groups, okay? So if we have 500 samples, or 500 individuals in all of our groups, and we have 10 groups, 500 minus 10 is 490 would be our DF. So we take our SS error and divide it by 490, okay? Now we have MS groups and MS error. We can do our F test, calculate the variance ratio F. F equals MS groups divided by MS error. And this is really, really, really important. F is the test statistic that we use to do a hypothesis test in ANOVA. Under H naught, F will be close to 1, differing from 1 only due to sampling error. If H naught is false, or if we're rejecting H naught, MS groups should exceed MS error and cause F to be greater than 1. So anytime F is greater than 1, we probably have a significant p-value. The closer we get to 1, the less statistical power we have and the more uncertainty there is, and really how much different is, or how much greater is the variance of the groups relative to the variance of the error. Oops, pause my screen share there, sorry. Okay, so now that we know a little bit about how F works and the difference between F is a little bit greater than 1 and F is like 10, 20, 30, you can see that as we get further and further away from 1, we have a lot more confidence than our MS groups, which is quite a bit larger than our MS error, which means there really is a true difference. So think back to error and how we calculate type 1 and type 2 error. And we talked about that previously. And think about what happens if F is really close to 1 and we still have a significant p-value. It means we should be pretty careful. Okay. To calculate a p-value, as you may have heard, we calculate our F statistic, then we calculate the degrees of freedom for MS groups and MS error, and then we use the F distribution and several tables to find our critical value. So with ANOVA, because it's a little bit more complicated, we need both the DF from MS groups and the DF from MS error. We take our F statistic value and we look at multiple tables and our distributions, and we can eventually find what critical value of F we should have to have a significant difference. Or we can just use R real quick, and it's 1 line of code, no big deal. But here, if you're interested, is our probability distribution example for one-sided ANOVA. And you can see that we need F to be 3.52 or greater, given our degrees of freedom of 2 and 19 for our MS groups and MS error. And that's how we get a significant difference. Okay. So it's the same old thing that we've already seen with T and with linear regression, only instead of using T, we're using F. And F is also what underlies linear regression. We talked about that one. This is that stat. Works just the same way. Because ANOVA is just a special case of linear regression, where instead of having two numerical variables, we have a categorical variable and a numerical variable. Okay. So that's it. If you're really interested in the table, here's what you do. You look for your 2 degrees of freedom, and you line up both of them with F, and you get a difference, or you get a value, critical value, just like we saw. Now, this is really easy in R. You just do one line of code. Here is what happens if you run an ANOVA, testing the effect of species on, I believe, petal length. This is the same one we already did. You'll get a printout like this. It shows us the degrees of freedom for the mean squares and the sum of squares. Sorry, it shows the degrees of freedom for both mean squares groups, and mean squares error. So here's mean squares groups here, and mean squares error here. Okay, so groups are species, and there's 3 species, so the degrees of freedom is 2. Residuals is the total number of individuals in this case. So we had 147 there for our degrees of freedom for mean squares error. We get the sum of squares values. So sum squares groups, sum squares error, mean squares groups, mean squares error, this divided by this. So this 218 divided by 0.19 yields the F value of 1180 and a significant P value of 16 zeros and 2, 0.000006 times 16, 2, right? So very, 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 very low P value. So in this case, what I'm showing you is that when you get a table like this one from an ANOVA, which you do every single time you run one in R, you have all of the components necessary to back calculate or to check your calculation for your F value, which you can then also, if you really wanted to, grab the information you needed for your table and go check your tables to make sure your p-value makes sense. So that is why people ask you to actually show these tables when you publish data. When you're publishing your statistical tests, people want to see the table because they want to see what underlies your values. And they're really interested in this kind of thing. How much sample size did you have? And do you really have enough degrees of freedom to make any case for your argument? Cool. So we get this table. Now you understand what all the components are. You can take them and you can work with them to actually get your F value, which underlies your P. Now, F also underlies linear regression. And in both linear regression and ANOVA, we can technically have an R squared. R squared is used in ANOVA. We also see it in regression. We've already talked about how they're basically the same. R squared tells us the contribution of a group difference to the total variation in the data. So R squared, in other words, is the sum of squared groups divided by the sum of squares total for an ANOVA. We can then say the fraction of variation in Y that is explained by groups is some number. R squared is always between 0 and 1. Close to 0 means that all the groups are very similar. Most of the variability is within groups. Close to 1 indicates that groups, the explanatory variable, explain most of the variation in Y. We can calculate R squared from a table. We can calculate it in R. It is not in our table output when we run a summary of AOV because it tends to not be the thing that we're focusing on. But if you want to learn how to do it, we can talk about it in lab. I've already told you this, but we can run ANOVA when we have 2 groups as well. And it's the exact same thing as a two-sample t-test. So we finally have learned everything we need to understand this one thing. When we run our summary of AOV, we now understand what this table means in full. It means we did a bunch of complicated math, even though all we did was run one line of code to see whether there was an effect of Y on X. And what we ended up with is yes, there is in fact an effect of Y on X. So that's nice. But now that we know there's a difference, we don't know which groups are different, what the magnitude and the direction of the difference is. We have some good ideas from our graph, but we need to do statistical tests to tell us. we need a post hoc or after this test called the Tukey's honestly significant difference test. When you run an ANOVA, if you get any significant effects in your main summary table, you must run a Tukey. Okay. So let's talk about Tukey. After we run an ANOVA and see a significant effect, you have to have one of those or else you can't evaluate your Tukey. We want to know the direction. We want to know the magnitude. The graph tells us a lot. We've already gone through all of this. We're going to run a Tukey's honestly significant difference test. And what this does is it basically runs pairwise t-tests between all of your groups and all of your other groups to tell you who's different from who and in how much and in which direction. Tukey requires the following. We need the mean of each group, the mean squared errors, the mean squared group, the sample size of each group, and the degrees of freedom of error. It relies on the Q statistic and the Q distribution. So the Q is slightly different from the F, slightly different from the T distribution. And you calculate Q as y hat I minus y hat j divided by the standard error. Y hats are means of our two groups. SE is the square root of the mean squares error times 1 over ni plus 1 over nj, where ni and nj are the sample sizes of our two groups. So you can see it's quite complicated, but now you have the math. We compare a calculated Q to the critical value for Q in the Q distribution at alpha equals 0.05, our standard cutoff for these kind of things. And that tells us whether we have a significant difference. So we can do all of that, or we can just write Tukey HSD, name of our data frame, and R, which we prefer. But now you have seen what the math looks like. When we run our Tukey, you can see just how simple it is. What I show you here is all of the code necessary to do an analysis of variance in R. It's 1, 2, 3 lines of code. That is it. We ran our model, our analysis of variance. We summarized it. We see a significant effect. We go, I wondered more about that. We run Tukey HSD on our data. We get our table. And it spits out all of the species compared to all the other species. So let's have a look. Versicolor minus Setosa yields a difference of 2.798, indicating that Versicolor is quite a bit larger than Setosa. I look at my graph. That's true. It then tells me the upper and lower bounds of the comparison and a p-value, and 0 is basically is the same as this. 2e to the minus 16 and 0 are roughly the same. So it's less than 0.05 because 0 certainly is less than 0.05. So Versicolor to Setosa. Versicolor is bigger, it's different. Virginica to Setosa. Virginica is much bigger, it's significantly different. Now, the interesting one was this comparison. Virginica to Versicolor. Virginica is bigger and it's different. Okay, significantly different. So all 3 groups are significantly different from all 3 other groups. And now we know Virginica is the biggest, then Versicolor, and then Setosa is quite a bit smaller than the others. So really simple to understand how to interpret. The math behind this really simple statistic is actually quite complicated, as we've learned. So there's our sample all the way through. Here's what you need to know about Tukey. It's a conservative test, meaning that the real probability of making at least one type 1 error, which is rejecting a true null, is smaller than the stated alpha of 0.05. When sample sizes are equal across all groups, we have a fully balanced design. The p-values are exact. There's actually no error. So that's neat. For our test above, n equals 50 for all 3 species. So we actually have exact p-values here. And we know n equals 50 for all 3 species because the residuals here are the mean square, the degrees of freedom for the error term is all of the samples minus the number of groups. So that's 150 minus 3 is 147. So these p-values are exact. There's no error. So this is a really robust assessment. Okay, so I'm going to pause. This is how you do a one-way ANOVA, the effect of one variable on one other variable. That's great and all, but usually we don't only have 2 variables in isolation. We usually have lots of other things that are being measured, especially in the environmental sciences when we're out in the field. We must account for them. And there's complicated modeling, linear modeling, things like that that we're not going to get into this semester that you can come talk to me more about in my office anytime, that are more often used to handle this large amount of data. But ANOVA and linear regression can handle multiple variables pretty easily. Once it gets too complicated, it's time to do a different kind of scheme for modeling, but we can do multiple variable effects with analysis of variance. We're going to go through an example now. We call this a two-way ANOVA. Everything we've learned so far is just the effect of X on Y. But we can assess multiple variables in several different ways in a two-way ANOVA. So for example, what if we are interested in the effects of X and Z? We can have as many ways as we want to. For those of you who are from where I'm from, this is kind of like how you pick out a cheese coney at Skyline. The more ways you add, the more toppings you get. Maybe that makes sense for 0 people. That's fine, but that's part of my culture. So here we go. It can get a little hard to interpret this kind of analysis, which is why we switch to different styles of modeling if it gets too complex, but I'm going to do my best to help you understand this. Here's a two-way ANOVA. Really importantly, the most important aspect of all of this is when you do a multiple way ANOVA, it's important to pair a meaningful graph that shows the ways with your statistics. If you can't visualize the hypothesis test with your graph, it's not a super great graph, right? So we're really interested here in our penguin data and understanding what is the effect of both species and year on bill length. Do they affect the data individually? Do they affect the data interactively? And I'll talk about what that means. Here's my question. Does bill length vary by species and or year in penguins? In this case, I've made year into a factor. So we have just 3 bins of groups. So 2008, 2009, and 2007, and 3 species, Adelie, Chinstrap, and Gentoo. They're both factors. So we can write this formula in multiple ways. If we write y tilde x times z, we're interested in the interactive term. What happens as year varies and species varies? Do they interact? I could also test x plus z, and that's an additive model. What is the effect of x, which would be species, and what is the effect of year? So it would be both of them in isolation and not when they're both happening at the same time. Now, both happening at the same time is much more likely. So that's what we're going with. Okay, so we can see we ran our interactive model, two-way ANOVA, and we got significant effect of species. There is a difference between bill lengths within, there's a difference in bill length between species, okay? Now, there was no effect of year, although that p-value is close to 0.05. So that would then say that we would reject the hypothesis that there was a difference, or we would fail to reject the null that says there is no difference in bill length by year. Now, what we're really interested in here is the interactive effect. And I can show you why. The interaction of species and year says the following. Within a species, the H naught, within a species, there is no difference in bill length by year, right? So we can see that's probably accurate. There's maybe no difference in bill length by year. That's our H naught. We would fail to reject that H naught given that our p-value is 0.5481. Now we can run our Tukey if we want, and if we do, it'll only tell us how the species differ from one another. It will not be able to tell us, it'll spit out data on these, but we can't interpret it. We can look at an example in class. So this is an interactive ANOVA. It's pretty simple in this case because there's a bunch of stuff that isn't significant, right? But hopefully this makes sense. And this visual hopefully shows you what interaction means. What is the effect of X and Y varying at the same time? So within a species, is there an effective year? Yes or no? And is it different for each species? That's what we want to know. All right. Just to quickly unpack, for multi-way ANOVA, we have to decide if we want interactive terms or not. Using the asterisk or multiplication sign, we can do interaction. And if we just want the 2 variables separately, we can do additive with a plus sign. Okay. Here's the 2 different tables. The interactive term adds this interaction of species and year. Whereas if we just do them separately, we only get the effect of each one on its own. We don't see what happens when they're interacting. Sometimes interactive terms make things too complicated. Sometimes our hypotheses aren't asking for that. Sometimes our terms shouldn't or can't interact. We want to think about that when we're making our model. All right, so again, interpretation. We saw the effective species was significant in our main model. The effective year and interaction of the two is not. So when we look at our 2 key, we can only consider the difference between species. And our 2 key is still going to print out all this stuff, right? And it gives you these nice lists. Tells you the effective species here. We can interpret that. The effective year, that wasn't significant. We can't interpret that. The effective species and year, we can't interpret that either. So all of this is not useful. We have to direct our eyes to the useful stuff, which is right here. And that's it. On to the next. What if the interaction term is significant? In this case, we need to be careful. It means that the relationship between y and x is dependent on levels of the factor z. In our example, that means that the penguin bill length would differ by both species and year, and the relationship between bill length and species would also differ by year. When the interaction is significant, the interpretation of the main effect, just the effect of y and just the effect of z, is incomplete or misleading. What that really means is that when you see interactive terms that are significant, you should try to interpret that interaction first, because it tells you a more complete story than the individual variables in isolation. And we can show examples and talk through this a little bit. This requires practice. It requires kind of melting our brains a little bit. It can be a little hard. We will learn. Let's talk about interactions. Here's an example. This comes out of the Whitlock and Schluter textbook. And what we're measuring here is we're out in the intertidal, and we're measuring the effect of herbivory and tidal height on surface area of some plant, some marine algae, let's say. Okay, so what is the effect of herbivory? What is the effect of height, tidal height? So are you high or low in the intertidal? And what is the effect of the two interacting? Herbivory is either there, it's absent or present, and tidal height is either mid intertidal or low intertidal, right? So let's look at the graph first and see what we can see. Here we see that there's a significant effect of herbivory on the surface area. Herbivory, significant effect of herbivory on surface area. So let's check for that in the graph. Herbivory is here. If there was an effect of herbivory on surface area, what we would see is the grand mean of everything that's here, which would be like this. And the absent treatment would differ from everything in the present treatment. So if we took our means, we'd be comparing these two grand means that we can't actually see, but we're having to like kind of interpret. And we would say, sure, the presence of herbivory seems to drive down the surface area. Maybe, right? Okay, so that's how you interpret just this first bit. Now let's look at height. Just height in a vacuum. Is there an effect of height, tidal height, on surface area? And it says no. If there was an effect of tidal height on surface area, what would happen is we would compare the mean of the red to the mean of the black. And that is probably going to be a red mean here and a black mean kind of here, right? We don't consider this part at all. We're just looking at the mean of black and the mean of red. And we would say, are they different? And the answer is like, they're not different. It looks like they're actually maybe different, but because the black in particular shows so much variation along the y-axis, it's really, really difficult. We're going to get error bars like really big, right? In other words, our F value ends up being really low. Our P value comes out as not significant, right? Whereas before we had an F of 6, which is not great, but it still tells us that there's 6 times more difference between groups than within groups. That's pretty good. So we see this is significant, this is not, but, and this is where things get really important. The interaction term is significant. And this shows us why we care about interaction above individual terms. So let's see if we can understand how that works. If there was going to be a significant effect of this interaction, what we would see is within an herbivory treatment, there would be a difference in surface area between mid and low. That would mean this is different than this, and this is different than this. We see that. We also might see that there will be a difference in the effect of herbivory treatment, of tidal height across herbivory treatments. Low intertidal without herbivory, high surface area. Low intertidal with herbivory, really low surface area. Versus in the mid intertidal, it doesn't really matter. Surface area is surface area. This difference in relationship across the treatments in the effect of the tidal height is an interactive effect. Now that, I'm certain, is confusing, but that's what we're looking for. If there's an interaction and it's significant, within an herbivory treatment, there is a difference in height, in the effect of height, and that is true, right? We see this, and even that they're switching the relationships, right? So not only are the two tidal heights different within an herbivory treatment, but the relationship also reverses itself. So that's pretty interesting. We're going to work on more examples of this in lab, but this is how you analyze real data, right? It's never as simple as the penguins data set. The penguins data set is real data, but it's also an example case. It's never that perfect. This is more likely what we're going to end up looking at. If you can understand and interpret this, you have completed basically all the learning goals for this class. And if not, we can keep working on it. It is okay. Okay, so I already showed you all of this. So if you are like, I didn't understand what he just said, look at these hypotheses and see how they compare to your understanding of this graph. And I'll leave it there. This is it for today. And this is our last video lecture. So thanks for bearing with me while we went through these. I hope they were helpful. And now they're a resource for you as long as they exist on the internet, which hopefully will be a while. Thanks for your attention, and I'm super open to your feedback, as you know.